First of all, I apologize for the font. It seems to have screwed up, but that's fine. We'll just carry on from that. Trends in mechanical design. This is great that we're having a mechanical afternoon or a morning for you guys. TMP is a mechanical engineering firm. We're head office is in Toronto. We have a couple of satellite affiliate offices. One's in Calgary, and then there's another one in Boston. And you know, we've been around for over 50 years now. I guess we're approaching 60. And we have focused on mechanical design, and we dabble a bit in some civil work, and we do some commissioning work as well. One of the things that we do, and one of our proven track records, is listening to our clients and what our clients' needs are. And we were one of the first large-scale mechanical companies in Canada to adopt BIM, and we've been doing this now for, I guess, five or 6 years. We are now almost fully BIM in our office. At least that's the attempt that we're trying to do, is to try and get away from 2D work. Although we can't completely break away from it, we do try to do the majority of our work in BIM. We're certainly not new to this. TMP has been a force in the mechanical design, looking always at innovative solutions, and certainly looking at sustainable solutions to situations long before sustainability ever became a buzzword in the industry. So we've developed a couple of industry standards or design practices that have become industry standards. One of them being compartmental units that are used in almost every office tower in North America now. We had a lead hand in developing that back in the 70s. And another innovative solution that came early 80s was this pre-coil-recoil arrangement that you'll see in some of the Calgary projects that we've worked on and some of our other office buildings in downtown Toronto. Don't necessarily want to get into that. But essentially what we do is we recover a lot of heat or a lot of energy in the fresh air streams. It's a very efficient way of recovering heat in the building, and it's become very efficient way of reducing the amount of energy that's used. A bit about our BIM practice. This is an image of the Canadian Human Rights Museum in Winnipeg, and this was the first project that we cut our teeth on using Revit MEP. We started this project back in late 2008. We were using either the second or third iteration of Revit MEP to do this job. And at the time, none of us understood what we'd gotten ourselves into. It was probably one of the most complicated project geometries that's ever been worked on. The only one that I can think of that equates to this is the Royal Ontario Museum back in Toronto, and you see if you've ever seen it, there's all these sort of, looks like a bunch of cubes that have all been turned on their side. There are very few 90-degree angles in this building. The only ones I can think of are the elevator shafts, and anything else is pretty much on a kooky angle, and that's how the architect wanted it. And there really was no other way to design or even construct this building other than using some sort of 3D modeling software. So we were willing and able to jump in, and it certainly been a bit of a roller coaster, sort of adapting our practice to work in BIM. I remember some of the earlier drawings, and these are images of some of the very first Revit MEP elements that we put in that model. There was a piece of ductwork that wrapped around the top of that glazing that you just saw in the last picture. And this other bit on the right in the bottom corner was the first plumbing that we tried to, all the plumbing connections that we tried to make. And this took us about a week to figure out the Revit MEP and all the connections, and more importantly, the slopes of all the drainage piping. And even to this day, sloping the drainage lines is still one of our single biggest issues that we have to work with using Revit MEP. It's not very simple to move a sloping drain line one direction, 3 feet one way, 3 feet the other way, because it impacts the slopes of all the other drains that connect to it. And it's gotten better. Revit MEP has gotten better at this, but it is still quite a bit of a challenge to work with that. Now, I use these images because it was after that first week of working on those connections for this battery of washrooms or battery of lavatories that we got through it, and we said, you know, we can do this. We can work in this. We can further. We were satisfied that we knew enough about what we were doing, and that we had our workarounds, and that we could work in BIM. And you know, 5 years later, the museum just opened a couple of weeks ago, and it's a great success. The building is phenomenal, and the model was a tremendous success. Using that model was a tremendous success in resolving a whole bunch of coordination issues that came up on site. A couple of other uses. So there's projects that were never intended to go BIM, but we ended up using the architect's model and our BIM capabilities to resolve a bunch of issues. So this is an image of the Club Regent Casino. There was in Winnipeg, there was a theater edition that was done, and the ductwork had to all be above a certain sight line and up within the trusses. And the acoustic consultant also had a whole requirement for duct velocity in the ductwork, and the two of them at times were incompatible with each other. And you see, we actually utilized the BIM model and our BIM capabilities to draw that ductwork and to thread all the ductwork through the trusses in order to make this thing work. So, you know, there are some sort of side benefits to having that BIM capability and that ability to deliver it to the client in a way that solved an awful lot of issues, or we were capable of resolving an awful lot of issues before it became a problem in the site. Here's a couple of other screenshots showing just how tight some of those connections were and how we worked in the roof drain with the ductwork and how it all came together. Couple of other projects. This is a smaller project. This is a Lexus car dealership in downtown Toronto. Again, if you look at it, it's small enough that when we strip all the exterior skin and the envelope elements away from the model, you can just see how, even on a small job, how complex those mechanical systems and the ductwork and the piping all can be. So that's the complete mechanical model with just with all the architecture stripped, or all the exterior elements stripped away. And even for just a small 3-story building, you can see that it can be quite complicated, and it can be quite an effort just to coordinate all that before it goes into construction. So there's tremendous benefit utilizing BIM and Revit MEP as a visualization tool, and that's primarily what we've been using it for, and a coordination tool. Moving on, some more current projects. This is the Deloitte Tower in Montreal. It's under construction right now. It's a project we're working on with PCL, and it's been going pretty good so far. I haven't heard any big complaints or issues that we've had to resolve. This is just a screenshot of one of our sheet files that's been generated out of the Revit model, and this was issued to the constructors or to the contractors to build from. We talk about the sheet files, we talk about the model. This was a sheet file that was generated out of the model, just to show how all of that does get represented on a sheet file. I'm sure a lot of you guys are familiar with this already. But again, for the mechanical rooms at the top of the tower, it becomes quite a bit of an interesting coordination issue to resolve all of these items. Here is another screenshot that was taken out of that model showing the coordination of the piping and the ductwork and the pumps at the top of the building and how the mechanical room was all going to come together. Again, this is another screenshot at the top. This one showing the pumps and the heat exchangers and the piping. All of it very, if you think about the way we used to draw these things in 2D, you would never have seen some of the level of detail that you see in there. All those fittings, all those connections, all the different elevations that piping and that ductwork has to occur on in order for it all to fit. Another project, another fairly recent project, this is the Ripley's Aquarium. Just opened up at the base of the CN Tower in Toronto. This is another job that was delivered in BIM. This was another challenging project. There was an awful lot of piping that goes along with the aquarium and the tanks. If you can imagine, it's not just chilled water and water, plumbing connections. There is an awful lot of other services that need to go into maintaining these types of aquariums. This is all salt water driven as well, so there's a lot of material issues that we had to consider as well. And again, we delivered the model in BIM, and it was a tremendous success in terms of resolving a lot of coordination issues ahead of time rather than try and resolve them all in the field. And you see some of the mechanical rooms and some of the mechanical equipment that we would model in that in order to support the aquarium and all the maintain the life support systems. They're called life support systems for the aquatic life in the tanks. And there's a shot of the finished product, how that all came together. The Bay Adelaide Tower is another project that's currently under construction in Toronto, and this is an interesting one, only because it drives home one of the points that I'm hearing a lot of people make in this conference in the past couple of days. The transition between the design model and the construction model is a fussy one, and what we're experiencing is a reluctance on the part of the constructors and the trades to take the mechanical model anyway, and they have a very hard time extracting our geometry out of the model and utilizing it in any fabrication models. Now, so what that means is either they look at our model and say, geez, that's pretty, geez, that's really nice, but it's all not very useful to us. And what they end up doing is retracing everything we've drawn in Revit in some other software. Trimble is the example, is probably everyone's most familiar with. But that's not something they can take and open our model in Trimble. They actually have to redraw it. So in the case of Bay Adelaide, what happened was they took that and they redrew it, but they didn't necessarily follow our drawings. They drew it themselves the way they thought it was going to fit and the way that they thought it was going to better serve their purposes, because they cut out some sheet metal fittings, they cut out some pipe fittings, and there was some what they thought was going to be some increases in efficiencies on their side. And what it ended up doing was messing up a whole bunch of the coordination that had been done in the model, in the design model, between us and the structural engineers on the job. So by not following our model, they ended up creating more havoc for themselves than they'd ever imagined. That's just something for all of us to consider when we talk about how that model transitions. The next couple of shots I heard the term BIM porn yesterday. These are just some great shots of how we managed to peel the skin off the building, and you can see at the top of the building some of the mechanical elements in that mechanic room. There's a louver on the outside wall inside that parapet, and all the pumps and fans that are in there. Really, this is also a great visualization tool. You get to see how some of these elements in the model interact with each other, and you can also find clashes an awful lot easier. There's certainly the clash detection features in Revit, 360 Glue, and Navisworks are certainly all tools that our design teams use at some point or another in the construction or in the design process and fabrication process. This also illustrates some of our practices, some of the BIM practices that TMP utilizes. I mean, we have this big office tower, Brookfield Place. This is the example in Calgary. And on the image on the left is the entire building with the skin on, and then we've stripped the skin off of it, and then we've even stripped the structure and the architecture out of it just to show you mechanically what's in that model. Now, interestingly enough, we have an office tower, say 50 stories high. We don't necessarily model all 50 stories. All 50 stories are similar in nature, so we pick 3 or 4 stories, and those are the stories that we model. We model the cores and we model the risers, but individual floor layouts, we actually don't model everything. There's a reason for that. Once we model, if we throw everything into the model becomes very difficult to manipulate. And regeneration times increase. So the less information that we actually need to put in the model, believe it or not, the better off it is sometimes. And this is an example that we're trying to illustrate on that one. Here's another shot of Brookfield Place with skin on the right, or sorry, on the left, and with the skin off. And you see some of the mechanical elements sort of at the underside of that piece of structural steel, and then the washroom core further behind. And again, here's a stripped down screenshot out of the model showing the mechanical elements around the perimeter of the building, the heating elements around the building, some of the fan power boxes that are in the raised floor, and the concrete cores sort of in the center, and all the servicing that goes around that. This I'm going to have to apologize for. I've come to a couple of these conferences where the architects and the structural engineers are showing us all these fly-through models, and it all looks really impressive. I thought for once the mechanical guys would have this fly-through model, and it actually, we couldn't get it to work this morning, so you'll just have to believe me, it was a fantastic fly-through model. Showed all the mechanical coming together. It was awesome. If you want, I'll show it to you on my laptop afterwards. Clash detection, I talked a bit about this before, but certainly clash detection is a phenomenal benefit to using BIM. We run it internally. We like to make sure that we have all the mechanical stuff sorted out before we go to our meetings. Hopefully we get it all sorted out. God knows our hands are never 100% clean sometimes. So we try and resolve our conflicts internally, and then we come out and we resolve everybody's together. We resolve all the design team's conflicts. And then, as the design progresses into construction, it brings on a whole new level of coordination when we start getting in other people's models. So, for example, we would have been working, the Human Rights Museum is the example I'll use. We were using the Halcro-Yali's steel model for design purposes, and at one point when the Walter steel model became available, we pulled that out and we dropped the Walter steel model in, and lo and behold, there was a whole bunch more coordination issues that needed to be resolved. But like I say, this is a great coordination tool, and before this deal arrived, we had resolution to a whole bunch of those issues rather than have it arrive and then stand there scratching our heads on site. So there is a tremendous benefit to using this. This is a project we're currently working on. This is a collaboration between Ellis Don, Dialogue, and ourselves. This is the Union Station project in Toronto. The image on the left is a point cloud image that was shot by Ellis Don for us of the existing as-built condition. We modeled the 2D drawings that were produced as the base building drawing. The whole point of this is we were retained to do the fit up for the retail spaces, and if you guys are familiar with retail, the word there is keep the ceilings as high as possible no matter what. So we ran into some conflicts, so we needed the 3D model to try and resolve those conflicts before we actually started committing forces on site. Here's an example of that. How you see in the image on the right, there's a duct sort of penetrating another duct that was never visible in the 2D model, but became apparent when we drew it in 3D, and also how it was resolved in how it was constructed in the field. You'll see in the point cloud data, or in the point cloud model, and this is one of these areas where we're looking at how we resolve it. This is still a work in progress. So the other thing that I came here talking about, and everybody talks about this level LOD, and you have to bear in mind that there are two LODs. There's a level of development and there's a level of detail, and the two are not one and the same. You can have a very early level of development and have a huge requirement for a level of detail, and that level of detail, if you want to put that level of detail into a model early on in the development, you're only kidding yourself. That information is probably not very good. So we came up with following, I think, a British standard. We talk about IG, which is an information grade. And I think the CAN-BIM is adopting this idea of information rather than level of detail, so that at schematic design, at design development, at construction documentation, you actually have a different level or information grade depending on the level of detail or where you are in the design process. I'm just sort of throwing that out there as an idea, only because this is an internal document that we have developed and that we sit with architects and owners saying, you know, okay, at SD, this is what you're going to get, and at DD, this is what you're going to get. So, I mean, just looking across the top row there, air terminals, if you look around diffusers in the ceiling, at SD, we wouldn't be showing that, but at DD, as the ceilings start to get developed, we would start showing them, and certainly at CD, we would as well. So that information grade is a term that was coined, I think, by the British standard, just to separate, you know, what LOD from information availability is, and just to keep that in mind when you're looking at that there are two different LODs, and they are sometimes confusing. Changes to our internal workflow. This is a great image. This is our BIM manager scribbled this down. I said, you know what, that's exactly what this is all about. He was going to try and pretty it up for me. I said, just leave it, because it really illustrates the point really well. If you look at the image on the left, that is the entire BIM model with all of the linked files into it, all the architecture, all the structure, everybody's stuff. Mechanically, you know, our files occupy a very small slice of that pie. And if you look at the image on the right, which is that small slice of mechanical, what we do is we divide that pie up again even further into work sets. At first, in our first iterations, what we were doing is we were creating separate mechanical models on large file jobs. So we would have a BIM model for sheet metal, we'd have a BIM model for piping, and we would have a BIM model for plumbing, for example. And what we were finding was even that was becoming unmanageable on some of the bigger projects. And what we've done is we've gone in and we've even pared that down and just said, okay, work sets. And even still, some of the architectural firms that we deal with, they're asking us to break the models down into multiple models, and we were having to sort of issue or talk about being a bit more resistive to that idea, saying, why don't we look at the way work sets are developed, or work in these work sets, and it just becomes a lot faster to work for us. The regeneration times in the models a lot quicker. It certainly it allows multiple people to work in the model simultaneously as well. So certainly keep that in mind. This is something that's certainly benefited us. Training. Training has become our single biggest issue internally. We actually have a very structured internal training program. What we've done, what we've developed, is a whole series of videos of, there are 4 that are shown on the screen here. There's certainly a lot more than that. There's, I think, we're getting close to 50, I think. So, so for the novice modelers and even the guys who need a refresher, you can go in on our internal server, and there are basic trainings on BIM 360 Glue, and you can watch these little 10-minute videos that sort of explain to you how to get in and around using BIM 360, how to utilize the clash detection tools, how to attach a file, how to detach a file. So we have all these little learning modules, and we're actually able to keep track of which of our modelers have seen which of these videos, which are the ones that are the ones that people keep going back to, because that's sort of telling us, where are people struggling. Without them telling us, we actually can see where those struggles are occurring, and maybe bring in some outside help to try and have a one-day afternoon learning session with these guys to try and straighten out some of the things that we see that they are struggling with, and having to go back and repeatedly try to understand what's going on. So this is another example about how to link a CAD file in. This is just more of the same thing. BIM 360 Glue. So this is one of the newer pieces of software that we have adapted internally. BIM 360 Glue is this cloud-based software where we load the model onto a cloud and onto the cloud, and what happens is designers and the modelers both have access to this, and they can pull down the model and they can make SketchUp comments in the model, and then reload it to the cloud, and then our modelers back in the office can actually see these comments. So if you picture yourself as in a coordination meeting in an architect's office, and something needs to be moved. We can sketch it up in BIM 360 Glue there on the spot, throw it up back on the cloud. The modeler back in our office can actually pick up those marked up comments, make the changes, and then reload the model, all in the same sort of real time. And it actually has been a tremendous benefit. 360 Glue also has some clash detection capability, certainly reduce waste. When we say waste, I mean it certainly improves the efficiency of our practices, because there isn't that sort of wait time between coming back from the architect's office, downloading all that information, and then having it all done and then go back the next week. It's all done fairly quickly. So this was how this efficiency was described to me as by our modelers and our designers, saying this is how this workflow process works. Is we take this 3D model and we generate a 2D sheet, and right there, going from 3D to 2D, you've actually lost some information. We mark up the 2D sheet and we hand it back to a 3D modeler, and he looks at the 2D sheet, and already there's some sort of loss of information in the interpretation there. He's got to puzzle it out and figure out how to make it work, and he generates the changes in the model and generates another 2D sheet, where again, his ideas have now been lost in the translation from 3D to 2D. Back to the designer. The designer looks at it and he has to puzzle over the 2D sheet and then mark it up again, and then either it's been resolved or it's not. So that's the idea behind this workflow. So what we get with 360 is that markup, that sort of compression from 3D to 2D, and that loss of information, is that process has been bypassed. I mean, we're marking up the 3D model we're marking up a 3D, we're marking up a 2D surface in the 3D model, and the information actually becomes an awful lot easier to understand that way. And I do have an example here. This is a sample. We were sitting in an architect's office, and we were told that the standpipe that we had running in the exit was encroaching on the exit width, and you know, the solution was to push the wall there on the left further out, and that way we can push the standpipe further away, and voila, the exiting distances have been resolved. So that was all done marking up a 3D model, rather than having to try to mark up a 2D sheet to try and explain it. We would have to done that in a couple of different sheets to try and show what the issue was. So, I mean, the problem became very apparent in the 3D model, and the solution also became very easy to relay back to our modelers what the solution needed to be and how it needed to be changed in the model. And that was all done like I said, in a markup that got in an architect's office, back up to the cloud, and then back down to our modeler, and he had it done fairly quickly. I won't say in the same day, but it was all done very quickly. Interoperability issues. This again, this is the Bay Adelaide project that I showed you before, and this was the issue. We had this whole bank of plumbing fixtures all drawn up, and they ignored all of it. They redrew it themselves, and they created a whole bunch of problems with penetrations through the shear walls that the structural guys had not allowed for. So this is a common theme, and this is one of our biggest issues, is how we manage to utilize the geometry that's in the model, rather than just have it be a pretty picture that everybody can go back to and have a look at to see how was that pipe supposed to run, or how was that dike supposed to have run, so that all these issues of interference were resolved. We would really like to have them take that information, take that geometry out of the model, and utilize that in the fabrication process. And so far as I know, it hasn't been done, although yesterday, the guys who had that they're up here. They seem to have had some software that they say will work to do this. That's why I come up to this Building Smart, which is the standard that's been developed, this IFC standard, which is there is this standard for industry foundation classes, which basically, if it follows it, you should be able to take the geometry of what's been drawn and transfer that information back to a different party, and they should be able to use that in their own software. In our case, it would be Revit MEP, and then take it and use it in a Trimble software to try and develop fabrication drawings. Now, what I heard yesterday from the guys who were up here presenting, and I have yet to see it, and I'd really love to go over there and have a look at it, is how they say you can, through the Navisworks model, they can generate an IFC model that then can be extracted out and taken into a Trindle model, and they could generate that. So hopefully we're there, that there is some sort of software available that can do some of this stuff now. But what it says there at the end in the bold is the barrier has been vendor implementation within the proprietary product. Hopefully we've sort of crossed that boundary now. I really hope we have, because it'd be a tremendous benefit to the trades. This is a great little sample piece of software that we internally are now starting to embrace. And I'm going to take you through this sample. This is a third-party software we downloaded from Takeo Pumps. And you're going to have to follow this because we didn't understand it until we started using it. But this is a very powerful piece of software that we use during the schematic design process. And I'll take you through this. What we've done, and this is the airport crossing project we're doing down in Calgary. It's not a very big project, and that's why we sort of started with this. And what we did was schematically mapped out the cooling plant. So in here you'll see things like the cooling tower, the chiller, a whole bunch of pumps, and the coils representing the cooling load in the building. Now, what you can do, and I'm going to take these two coils here as an example, is you map in into this for Calgary, you know, the location, the temperatures, and all the rest of it. And you've also inputted all the coil information, the loading requirements on the coils, like how much of a cooling load is represented by those two coils. But you can also go in and you can change that. So if through the design process the load on that increased because, you know, we're going to, that floor is going to become a data center or not, or you know, we're going to change that to a kitchen or something like that, you can actually physically go in and you can change the properties. And when you do that, it actually changes the pipe sizes for us. I don't know if you saw that, but it changed those lines to a 6-inch from a 4 to a 6. Similarly, that coil on the bottom, we could change that, and the pipe sizes automatically change in this software as well. So it picks this up based on the criteria that you put into it about how you want that piping size, and it learns, and it develops all of this. Now, what we can do then is we can take all that information and we generate a file, and what it does is it goes online, and because it's the Takeo vendor, what it does is it goes out and it sized all the equipment for you, it sized all the pumps, it sized all the valves for you, is it goes back online and it finds all the families for those pumps, and it extracts them off the internet and creates a file that you can now download into the model. And now we have all the families for all those products that we just got to drag and drop into place inside the model, and then we connect it up with all the piping. So it's fantastic that way, and we've used this small project, and we're very happy with it. And I'll put it up there, and the best part of this, wait for it, it's free. So by all means, go out and get this. I highly recommend it, and I've got, if you want to pick this presentation up off the app, you can. I've put the link in for the Takeo Pumps, but you'll just type in Takeo Pumps and it'll take you there, and you can find this very quickly. BIM next steps. So I've talked a lot about, and everybody in here has talked a lot about making better use of the geometry. Certainly internally, training and development of our modeling staff. We're going to expand that to include our engineering and design staff. Certainly utilizing those pieces of software that I talked to you about, showed you there about that. That was actually something that was initiated by our younger engineering staff, and they were showing this to me, and I actually thought it was pretty impressive. So we're going to expand that into some of our design staff as well, so that they can start utilizing some of this in the modeling. Continuing to work toward integrating our BIM engineering practice with third-party vending software. So I don't necessarily want to limit it just to that pumping software, but certainly load calculations, we've been dabbling in some of that. We still have issues extracting information out of the model. All you architects in the room, we actually rely on how that model is constructed in order to extract some of that geometry out of it in order to do load calculations properly. And this is another thread that's been going through the room as well. Getting better clarity on model ownership at the time the model is turned over to the construction trades. So we as the designers develop a model and then we turn it over to the construction trades. But 3 months into construction, if there's a change that comes through, if the owner says, I want to add, a swimming pool somewhere, do we now, who now, which model does that change get represented in? The modeler's detail, or the designer's model, or into the construction model? That always becomes a very interesting question, and one we actually wrestled with at the Human Rights Museum as well when we got into the gallery fit-ups. A lot of the as-built conditions were different from the design conditions, so when we used the model that we had developed to illustrate the changes that were being made to do the gallery fit-up work, we were told that a lot of the ductwork and a lot of piping connections that we were showing were not actually in those locations and needed to be changed. So some thought has to be put into how that information transfer works. And certainly the other thing that we've been doing is, or trying to do, is making better use of the parametric data for the FM applications. So some of that detailed data that you saw in that third-party software, certainly pump models, motor sizes, motor frame sizes, a lot of that information is actually embedded in those families and can be of tremendous use to the FM guys when they want to go back in if a motor's failed. They just go back and click on it and they find out what that motor frame size was, so they can order that motor again. I think that's it for me. Just a couple of projects that TMP's worked on. I talked about the ROM, that's it in the top left-hand corner. Pearson Airport, Brookfield Place, War Museum in Ottawa. My favorite is the Atlantis Hotel in Dubai. And here's just a sample of our projects. We do big and small. Anyway, that's it for me. Any questions?
It's Mohib from Globally Training. Have you collaborate software like estimating software like Naviswork with RabbitMEP, so you have a good idea about or good optimization between cost and design in the early stages of the project?
How much that optimization costs in order to do that? Is that what the question was?
Like it's a continuous relationship between cost and on design, like collaborating or integrating Naviswork and estimating software with RabbitMEP, for example. So you have an idea about the cost at any stages through the design process. The cost differential isn't that significant. It's really the cost of the software. I mean, we would be doing that level of collaboration or that level of interference checks regardless of working in 2D or 3D. It just becomes much simpler in 3D because visually you can see where the clashes are. We are subscribers to Navisworks because the clash detection capabilities in Navisworks are that much greater, but that does not detract from the clash detection that is available in BIM 360 Glue and in Revit. We tend not to use the clash detection in Revit. We use primarily BIM 360 Glue. When we're happy, we'll do another check in Navisworks, and then we'll take it on to the other design team members. And we'll even run clashes using their models internally to see, make sure that the steels, or make sure our ducts and pipes aren't running through steel, or the electrical guys haven't run conduit through our ductwork. I mean, these are some of the bigger things that we tend to find when we do that. But in terms of a cost, the only real cost to us is that subscription service or the purchasing of that software. This is, in terms of man hours, we would still be doing that whether we'd be doing it in 3D or, well, it's certainly a lot easier to find in 3D than it is in 2D. Typically, we wouldn't have even done some of this before, but using BIM, we save ourselves an awful lot of time in the actual physical drawing of the pipes and ducts. And that time saved is time that we look at those clashes and how we resolve them. Awesome.